Ugh, tough problem, but we're going to get through it together. Okay, what we're looking at here is a AP Physics C electricity and magnetism question from 2008. It's the third question from that exam, dealing with the Biot-Savart Law. What we have here is a circular loop of wire and a big radius r, and it's carrying a current I. At a point P, a distance of half the radius above the wire, we would like to figure out a few different things here. And we're expected to express all of our answers in terms of r, I, and fundamental constants. And in part A, what is the direction of the magnetic field at point P due to the current in the loop? So up here, point P, what is the direction of the magnetic field? Well, since we know the current is running around the circle like this, if we use our right-hand rule here and we curl our fingers in the direction that the current is going, our thumb will point us in the direction of the B field. So by the right-hand rule, we see that our B field here is pointing up for us. Okay, so our B field is pointing upwards towards the top of the page. That's what's going on here. Okay, that's our B field. Now, what's going to get weird is we need to calculate the magnitude of this B field at point P. And this is where stuff gets a little wonky, a little difficult. So the first thing that we need to do is, since we have this run of wire here, the circular loop, we're going to be using Biot-Savart's law. And unfortunately, because that point doesn't actually exist in the plane of the wire, because it exists outside the plane of the wire, we need to use the full Biot-Savart law in this problem, which makes it a kind of a pain. Sometimes you'll see Biot-Savart's law written like this: dB, or a small piece of the B field, equaling mu naught I, the current running through your system, over 4 pi. And then this is the big term here. You'll have a dl cross r vector over r cubed. Now, what you're often going to see in these problems, and not every time, is that, but what you're often seeing, what we're going to see here, is that this dl cross r vector, that's going to equal dl times r times the sine of theta. And what we're going to see in this problem here is that the dl component, the small component that is running around this wire, is going to be perpendicular to r. So what we're going to see here is that sine is going to be equal to 90 degrees, or the angle is going to be equal to 90 degrees, and the sine is going to be equal to 1, which causes it to go away, which will cause this r to divide out with the denominator, so we get an r squared. Because of this, more often, the way I tend to see it, is you'll see Biot-Savart's law written as dB equaling the mu naught I over 4 pi, but then you'll see it written as dl cross r hat, which is a unit vector. It's the number 1 sitting there, but in the direction, divided by r squared. So we see that a little bit more often. So both of these are very similar to each other. That's what's going on there. That's why sometimes you'll see it as r cubed, sometimes you'll see it as r squared, but that's what's going on. A big thing in this problem was recognizing that that angle was 90 degrees between them, and we can just wipe that out. Okay. What we have to do, though, and we look at this problem up here in this diagram, we're going to see some things going on here. While we have a dl vector here, what we're going to see is that in order to get to this P position right here, this is some radial distance r. That's the radial r vector that we care about. And if that is occurring there, then we know that this B field that is being created here, this B field is actually being placed perpendicular to it. Okay, this is a small segment of the B field, dB. And what this means, if there is some angle theta here, we can actually prove, just some geometry time, that this angle on the inside right here is also theta. Okay? Now this is important because what we're going to see is that if I take this dB and break it up into its vertical and horizontal components, these horizontal components here, they're canned. Okay, they're going to cancel out in all directions. You're going to have the same amount pointing left as forward as back as into as out as right. So it's gone. These horizontal components are gone. What's going to matter here are these parallel or these vertical components here. And this vertical component is going to be dB cosine of theta, because that's the adjacent side there. Now, what the heck is the cosine of theta here in this problem? Well, this is theta down here. Theta is, for a cosine, equal to an adjacent over a hypotenuse. Well, I have an adjacent and I have a hypotenuse here. So this cosine of theta is actually going to be equal to r over little r. Well, what's little r equal to? And why are we setting this up? Well, you'll see momentarily, but little r is going to be equal to the square root by Pythagorean's theorem of big R squared, right here, plus the quantity of r over 2 squared. And when we work all this out, we're actually going to get, by common denominators and whatnot, we're actually going to get root 5 times r over 2. Okay, so that's what we get for little r, and that's what we get for cosine of theta. Now, why does this matter at all? What's going on here? Well, when we come back down to this bottom, what we're going to see is that dB equals this. And if we get rid of our r hat vector, because we know the sine component's going to equal 1, this is going to equal mu naught I dl over 4 pi r squared. Okay? Well, we don't want dB. What we wanted was dB and then the parallel or the cosine component of it. So what we're going to have to say here is that the dB we really want is equal to mu naught I dl times the cosine of theta over 4 pi r squared. Well, we know what this cosine of theta is going to be. It's going to be big R over R. Okay, so we're going to take that and we're going to dump that in there. Now, this is where it gets long. We're going to have dB equaling mu naught I r over 4 pi r cubed dl. Now, in order to solve for b, I need to integrate both sides. Now, when you run this integral here, the integral of dB is going to come back as just b. And specifically, it's the b in the direction we are looking for. This dl vector, it's going to be the entire length of the circle. So that circle we had up top, what is the entire length of this whole circle? Well, that's just the circumference. And we know that to be 2 pi r. So we could show, working out some line integrals and whatnot, what's going to happen there. But you know that that's going to be the circumference of the circle. You know that's going to be 2 pi r. Okay? So what we're able to quickly say here, without having to do a lot of the tedious calculus, is that b is going to equal mu naught I r over 4 pi r cubed times 2 pi r. And it's big R here because that's the actual radius of the circle. Okay, so that's why we have a big R there. And at this point, you could technically just leave this here and you'd end up getting 5 out of 6 points. That's a fine final expression in my opinion. Depending on the years and depending on the graders, they may want you to simplify this, but I think this is fine right here. If you wanted to simplify it, we can. Throw the 2, get the pi, and then we start getting some really tedious stuff. We're going to get mu naught I big R squared over 2 and then R cubed. Well, what was R? R was root 5 big R over 2, and then that quantity is cubed. And honestly, I would stop there, but if you insist, well, let's just work out what this denominator is going to equal first, right? Our denominator is going to equal 2 times root 5 times root 5 is 5 times root 5, so it's going to be times 5 root 5 r cubed over 2, 4, 8. And that's going to equal mu naught I r squared. Oof. The 2 and the 8 becomes a 4, and since that's the denominator, I'm going to carry it up high. And what we're going to get in the end is 4 mu naught I over 5 root 5 r. And that is technically a fully reduced answer. Honestly, I would have stopped back here. I might have even stopped over here in the blue. Okay? But that was a long Biot-Savart law. The real thing that we were looking for was this cosine term here. We knew dl when we integrated it was just going to be the 2 pi r, but we needed to recognize that we needed the cosine term of that dB, that small piece of magnetic field, in order to get that vertical component, because that's what's going to be pointing out of the page there, or rather upwards away from our loop. Okay? And it continues. Now we've put a second loop, also carrying current I, added at a distance r above the first loop, so that this distance here in between them is still r over 2. Determine the magnitude of the net magnetic field B at point P. So we got to do the same thing again? Well, not exactly. What we should recognize here is that the magnetic field generated at point P is just the addition of the two loops B field together. And what we're going to see here is that since our B field from the top loop is going to be in the same direction as the B field from the bottom loop, we can just multiply the B that we had from the prior problem and just add it in here. Okay, so what we can do here is just, let's say, we know that our new B net, it's just going to be 2 times the B1 that we had previously. So our B1 we had was right here. We're just going to take this and multiply it by 2, because we're going to get that same field generated by the top loop and the bottom loop, acting in the same direction there. So, and the reason why these are in the same direction is because if you do it for the bottom, we got that this bottom vector was pointing up like this. If you do it for the top, that right hand rolls in the same way. Its B field is also running like this. So if we think about them running through the loops and through the loops, we're going to have the same quantity. These B fields are in the same direction. They're going to add together. So it's just going to be 2 times 4 mu naught I over 5 root 5 r, which just gives us 8 mu naught I over 5 root 5 r. So we didn't actually have to do anything there. We just had to multiply by 2. That was very easy. If this B field was running, or this current, excuse me, was in the opposite direction, then they'd perfectly cancel out and we get 0. So sometimes they'll ask you in that way for seeing what you know about your right-hand rules. Okay. And then we continue. Now we've got this diagram down here. We've got a small square loop of wire in which each side has length s. So the big thing is it's a square loop of wire and each side has a length s. Okay? And it's placed in such a way so that it's placed at point P with its plane parallel to the plane of each loop. We'd like to determine in terms of B and S the magnetic flux through the square loop. Well, this is nice because since this square loop is set up as it is, the flux is going to go through it. We're going to have a flux from the bottom one and a flux from the top one, so that's why we're using this B net from above. And if we want to find a magnetic flux, well, a B flux is just equal to the B field we have dotted with the cross-sectional area we have, which is the same as saying the magnitude BA times the cosine of theta. Now, in our case here, theta is going to equal 0 degrees. This plane of the field and the B field are acting in the same direction, and because of this, we don't actually have to worry about this cosine term. All we need here is to state that our flux that we have coming in, it's equal to the B net we had before. And even if we didn't know what that B net was, like, let's just put B net because that's what they're asking us to do. They say in terms of B net. So we've got B net, and then what's the area? Well, if each side of this has a length of S and it's a square, well, length times width is just S squared. And that's our flux. Woo! We did it. So that part wasn't bad at all. So the last two parts haven't been bad. It was just that part B. What we have to do now is the square loop is now rotated about an axis in its plane at an angular speed omega. Ugh. So there's an axis here, as we see, and it's rotating about it so that at some points all the flux is going to come through, and then at some points none of the flux is going to come through. And since it's rotating like this, when we have a change in flux, we need to calculate the induced EMF, that electromotive force, in the loop as a function of time, assuming the loop is horizontal at t equals 0. Well, we know that an EMF is equal to the negative change in flux in some amount of time. Now that's a pretty algebra way of writing it. If we wanted to write it a little bit more specifically and in a larger, greater mathematical way, we can say it's the opposite, because it's going to oppose that motion due to Faraday's law, of d flux over dt. So that's a small change in flux in some amount of time. Okay? And what is going to actually mess us up here is this angle theta. Before we said that that angle theta was going to equal 0, but that theta is now changing. So our flux is actually going to have a b s squared cosine theta term in it. So let's write that flux out this time. It's going to be that b net s squared, and then here's that cosine of theta term in there from that dot product. Okay? Now, what we can do, and this goes back to your mechanics knowledge, is theta, that's an angular displacement. Well, a displacement in general is a velocity multiplied by a time. So an angular displacement is an angular velocity multiplied by a time, so we can stuff that in there. What this means is that when we use this equation, the minus d theta, which is bs squared cosine of omega t now, dt, we need to take the derivative of this term with respect to time. And luckily for us, the b term and the s squared term, those are constants in this case. We can pull them out. We don't need to worry about them. The only thing that we need to worry about for our derivative is this cosine omega t. So what we're going to find here is that the EMF equals b s squared, and then we need to take the derivative of cosine. Well, the first thing we need to do is we need to take the derivative of this inner angle here, because it's respect to dt and there's a t on the inside of there. We take the derivative of omega t. Well, the derivative of omega t is omega, That t, remember, it's t to the first, so minus 1, t to the 0. And then now we take the derivative of that cosine. The derivative of the cosine ends up being negative sign there. Whoops, I'm missing a negative sign here. And then we get a negative sine omega t out of that. And then we find that our negatives make the positive. So a negative goes away and a negative goes away. Oop, bring the b back. And this is our final answer here, that the EMF equals b sine squared omega sine omega t. Okay, this is kind of similar to the generator equation that we saw in class, where the EMF for a general generator is going to be that WNBA sine of omega t. In this case, our n is just equal to 1, so it dropped away. Our area is just equal to s squared. So we already know that this EMF will be this WNBA sine theta, which is omega t. We just had to get there. And what we did is we just proved that using our flux equation. So not too bad there for that last part. The big part here was the Biot-Savart Law through the center. That was a lot of work. Okay. But with that, this problem, it wasn't that bad, and it is finished. So there we go, ladies and gentlemen. 2008, question number 3 from the Electricity and Magnetism exam. Hope you enjoyed it. Adios.